All right, AP Chemistry, here is your second to last most missed questions review. So the multiple choice review for thermodynamics is what this one covers, which is review number 7 on AP Classroom. Here's our first one to look at. It gives you a chemical equation and reaction, and then gives you a set of data here. There's two different trials. And the question asks you, how does the amount of heat released by each of these trials compare to each other? In other words, how does X and Y compare if we do this chemical reaction with these mixtures? Well, you'll notice the only difference is the volume of HCl that's added for trial 2 compared to trial 1, and it's doubled. And many of you would probably jump right to this conclusion that if you double the amount of reactant, you're going to double the amount of heat. That's true if this amount of reactant can react. Now, if we go back to our equation up here, we need 1 mole of each of these to react. It's a 1-to-1 mole ratio. So for trial 1, it's the perfect amount for both of them to get consumed because they have the same concentrations. But for trial 2, when I double the HCl, it doesn't actually change the amount that reacts. Because I'm going to run out of sodium hydroxide, this is my limiting reactant. It won't matter how much HCl you add. So X and Y are actually going to be equal to each other, the amount of heat released, because the same amount of reaction is occurring. There might be more HCl available to react, but there's not any NaOH available to react it either. So if you go through our problem and look at our choices, B is our only choice. They equal each other. And it's because the number of moles is the same in both trials. Now, if you chose a different answer for this by doubling that, it's true if you double it, as long as what you double can actually get consumed in the reaction. Our next one, a little cooling curve here. You've got water that you put into a container and you start to cool it off, and the student predicts that it's going to flatline right here, and they want an explanation for why it would flatline. Not right here. Looks like I'm looking at our temperatures here. It'd keep going down to 0, and then it would flatline because it'd start freezing. So part A is your correct answer. The molecules initially in the ice and the molecules initially in liquid have the same average kinetic energy. Let me see here. I think I misinterpreted this one. A student adds 50 grams of liquid water at 25 degrees Celsius to an insulated container. A student then adds 10 grams of ice. And then they're going to reach equilibrium. So they're going to reach equilibrium somewhere in between. So it'll keep going down, and then it'll flatline. And at that point, your amount of kinetic energy that's in the liquid water is equal to the amount of kinetic energy that came from the ice melting. Ice melting absorbs that energy, so they get to the same temperature. So A is correct. But for other heating and cooling curves, you do have that relationship that it drops down where it freezes, and we'll see that on another problem here. When water is added to a mixture, you've got this chemical reaction, and they want to know if you run two different trials. Here's our first trial, 7.8 grams and 3.2 grams, and then a second trial with 7.8 grams and 6.4 grams. Both trials yield the same amount of SO2, which the following identifies limiting reactant and the heat released. So what do I want to do? I want to figure out what runs out here first. So the limiting reactant is going to be the first step of this problem. If we have 78 grams per mole and we have 7.8 grams, this is 0.1 moles of Na2O2. And 3.2 grams, if you look up the molar mass of sulfur, it's 32 grams per mole. So this is also 0.1 moles of sulfur. Well, if I go to my equation here, I need 1 mole of sulfur for every 2 moles of Na2O2. So I need twice as much Na2O2 as I need sulfur. That means I'm going to run out of this first. So that's my limiting reactant. In trial 2, I double the amount of sulfur, and so I'd have 0.2 moles of sulfur. Well, that's not going to change my limiting reactant. I'm still going to run out of Na2O2 first. It doesn't matter how much more sulfur I give to the problem, Na2O2 will still be the limiting reactant. So if you go through your problems, we can already eliminate these. It's just our last two, C and D. So how do we get the correct amount of energy released? Well, if 0.1 moles reacts, we're going to use this value right here for the amount of energy that gets released for every 2 moles of Na2SO4. So this would be a stoichiometry problem, and I'd start with 0.1 moles of Na2O2, and then I want to convert out of moles for every 2 moles of Na2O2. I would produce 610 kilojoules of energy. And if you take 0.1 divided by 2, you get 0.05, and multiply that by 610, and you get 30, or really close to 30. And that's our answer right here for C. Here's our heating and cooling curve. So following questions relate to this graph. The graph shows the temperature of a pure substance as it's heated at a constant rate. An open vessel, substance changes from liquid to solid to liquid and then to gas. The substance is at the normal freezing point at time t equals 2. This is when you're heating up the solid, if you don't remember your curves. Then we're melting on this point. All the energy that's being added is not changing the temperature of the substance. It's simply changing the state of matter by breaking apart that crystalline lattice structure. This would be heating the liquid phase here. And then once we get to this point, it starts going from liquid to gas, which we call vaporization or boiling. And all the energy would be going to breaking the molecular bonds there, intermolecular forces. So this would be melting at t equals 2. That's what you should have chosen for that question. Our next one, we're given a chemical reaction. We're given that the delta H is less than 0. It tells us some extra information here. The value of the Kc for the reaction is 14.5, and it asks which of the following statements is true about the bond energies in this reaction. Well, you don't need to know your K value for this. You can just look at your delta H value. If it's negative, that means it's exothermic. And exothermic means that we're releasing energy. Now, the only thing you have to remember, does it require energy to break a bond or require energy when a bond's made? And the answer is when you break bonds, breaking bonds gives energy, or requires energy. Break bonds equals required energy. And when you make bonds, you give off energy. So what's the statement that's true about bond energies? Well, if it's exothermic, exothermic means release energy. And this is associated with bond formation. Now, all of your chemical reactions are going to have bonds breaking and bonds forming. So we're going to break the bonds on this side. We break these two apart, and we break our H2s apart, and we'd form all these bonds. So if it's exothermic, we release energy overall. The amount of energy I have to invest to break the bonds has to be less than the amount of energy I get when the bonds are formed. So if you go through these and read each one of them, C is your correct answer. The energy absorbed as the bonds in the reactants are broken is less than the energy released as the bonds and product are formed. And that's your correct relationship between bonds breaking, requiring energy, bonds forming, releasing energy, and it matches our delta H value to have an exothermic chemical reaction. That's it for this review. There's just one more review left, and I'll post that here shortly.